Oh, good call. Thank you, Bryce. I was muted. Happy Friday, everybody. Hope you're doing okay. Just wanted to try out the new emotes. There's a few. Here we have the Pog. Is there a workshop 3 or is it lab report thing time? It's lab report thing time. It is lab report thing time. What up, Lil Kev? When will the lab be posted? I'm finishing it up, and it'll be up tomorrow, I think. My one flex this semester, I have had no problems with getting anything into the breadboard. One may even say it's a butter board. Easy like butter. Okay, cool, cool. My board is not at all like that. It's been a struggle every step of the way. First lab is next week. That's right. For everybody, we're doing our first lab next week. Are there bonus points for making your lab report in LaTeX? No, but do it. LaTeX, if you guys aren't familiar, LaTeX makes beautiful documents with vector image text, meaning you can zoom in infinitely and still has crisp, clear lines. Having a hammer helps a lot. What? Zach says, I went to Harbor Freight and bought a small pair of pliers. I suggest you think about that. I've heard that suggestion from a couple people, and I think that's a very good suggestion. Where do we go again to sign up for our group partners in lab? There's a Google document. Check out announcements I've sent to the class via email, and you'll find a link there. If you've found a partner for lab, make sure to fill out that Google form. You have to fill that out, because I need to have a record of the groups, because you're going to submit the lab report as a group. That's why I need to actually make you a group within UB Learns. I spent more time not realizing that I had a faulty wire than I did on the workshop itself. Yeah, I ran into a faulty wire. I had one of my jumper wires actually kind of break when I disconnected it from the breadboard. Normal. It's gonna happen. Resume and cover letters in LaTeX. Very nice. Very nice. All right, how about we get started? All right, so let me turn this thing off. Turn the music down just a little. All right, so next week, we're doing lab number 1. And this is all about sensor calibration. And you're actually going to be calibrating an accelerometer. So when I post it, I'll give you more details about what the lab report needs to look like and when it's due. But generally, the report itself will be due 2 weeks after you do the lab. And this is for in-person students. Casper says, are we going to be assigned lab partner randomly if we can't find one ourselves? Yes. So what I'm going to do is I'm going to go to the Google form that everybody's filled out to make their groups. And then if I find that people aren't in a group, then I'm going to assign those people with other people. So you don't have to worry about it. If you don't want to go through the trouble of finding a partner, I will put you with somebody. But if you're an in-person student, this week during lab, you should have found a partner. So like, I think in-person labs are situated at this point. And if you're not situated with a lab partner yet for an in-person section, definitely going into next week, you need to find that partner immediately. And so just talk to your TA and they'll be able to set you up with somebody as well. So for the online students, if you're an in-person, do you still need to fill out the Google form? Yes. Yes, you do. If you're an online student, it's going to be 2 weeks after I post data for the lab. Or roughly 2 weeks. So I'll tell you the due date though. You found a partner, but I don't know his person number? Just ask him. And you can fill out that form. Okay. Let's talk calibration. I also have a cool story to tell you guys today related to calibration. We'll get to that at the end. Okay, let's talk calibration. So we established this last time. Sensors are transducers. They turn some physical quantity into something else. Usually they turn it into an electrical signal, so like a voltage that you can measure with an Arduino. So in workshop 2, we built a transducer using a photosensitive resistor and a voltage divider. So let's just call this a photosensitive transducer that we made. And depending on how you changed the ambient light conditions, and you can measure, like lux is a way of measuring light intensity. Workshop 2 was fun. I'm glad you guys enjoyed that. That's a fun workshop. So as you change lux, so this is a luminous flux. This transducer reacts to that physical quantity. And what it did is it changed the voltage across that 10 kilo ohm resistor. And that's what we were measuring with that jumper wire. And so I think the voltage, it had like the same shape as that luminous intensity signal, right? And now the potentiometer is also a transducer. What is it transducing? The angular position of the dial. So if you turned it all the way to one direction, it gave off 0 volts. If you went to the other direction, it went all the way to 5. So you could think of the potentiometer as a transducer that converts angular position into a voltage. Okay, so this is where calibration comes in. I'm going to pose something for you. Let's say that I am the Arduino Put yourself in the Arduino's shoes for once, okay? So I can only see the voltage. So how can I know the light intensity? Or the dial position? So from the perspective of the Arduino, all you're going to see is the voltage. How can I figure out what these physical quantities are? We're going to need some conversion factor. Erebus says if it's a one-to-one correspondence, then we can just scale lux to be voltage. Perfect. So let's write that out right here. So let's say that the light intensity is just proportional to the voltage that comes off. So here I could have a conversion factor. Let's call it X. And it tells me per millivolt that I'm reading on the Arduino, what lux does that correspond to? And then I can just multiply that by my sensor reading in millivolts. So as the Arduino, I see this. I could program into the void loop, hey, take that reading, multiply it by this conversion, and then, hey, you're going to know what the light intensity is. Same thing with angular position. You could find another conversion factor. Maybe I want it in degrees, and there's going to be another conversion factor. Degrees per millivolt times whatever that sensor reading might be. Okay, so this conversion factor gives us what we call a calibration equation. So a calibration equation is just a way to connect the quantities on either side of the transducer. How can I get a sensor reading in a voltage and interpret what the physical quantity that was coming in might be? Is that a nomer position? Angular. I a little sloppy. I'll admit, a little sloppy. Angular position. No, you're good. You're good. So this equation is not always linear. In the examples that I gave above, there's just a proportionality constant. Sometimes it's a little complex. All right, let's give a couple steps for the calibration process. So how do we go about getting a calibration relationship? And this is going to bring me to my story. Okay, step one. Apply a known external stimulus to the sensor. And this is external stimulus. It's just a placeholder for whatever type of sensor it is. Maybe it's light intensity, angular position, acceleration, force. Okay, but you have to apply a known stimulus to the sensor and then record the corresponding output. Which will generally be a voltage, at least in our case. Now we're going to get into this with my story, but applying a known external stimulus kind of creates a chicken or the egg problem. Because how can I apply like a known light intensity unless I have another sensor that's measuring the light intensity and I consider that sensor to be reliable, but how was that calibrated? We'll come back to this. Okay. So you're going to apply a known external stimulus and get the corresponding sensor output. Repeat this process using multiple known values over the range you intend to use the sensor. Yeah, no light. How would you measure no light? Over the range you intend to use the sensor. And then I think the best thing to do next is generate a plot. Just so you can visualize the calibration relationship. So let's make a plot here. This first one will be like the linear case. And if you're lucky, this is what your calibration looks like. On this axis, this is the physical... Oh, that's... okay. This is the physical quantity, which we're going to assume it's known. And then on this axis, we're going to have the sensor reading. Let's assume it's some voltage. So I try a bunch of quantities. Maybe I get something like this. And it's not perfect, but you can see I can describe that relationship between the two variables pretty well with a line. Sometimes it'll be nonlinear. I'm going to show you a typical pattern that might show up, where you keep increasing the physical quantity, but eventually the sensor reading kind of like remains the same, kind of like there's an asymptote there. So there might be situations where you like saturate the sensor. Maybe a pressure sensor where eventually you can't take any more load. And at this point, there's probably some structural breakdown in the sensor itself. But this one we can't fit with a nice line. There's some nonlinear relationship. It doesn't always behave the same. But even in this case, you might find a region of behavior that looks pretty linear. So like maybe over like this range of physical quantities, I could just use a line. Okay, so I guess I've already been talking a little bit about step number 4, but fit the data with an appropriate regression. It could be linear. Could not be. Depends. For a linear regression, you're going to have the physical quantity is equal to some like slope x times your sensor reading, maybe it's in millivolts, plus some y-intercept. Okay, this brings me to my story. We're going to talk about measurement standards. Specifically, the measurement standard for length. But I'm going to pose you a problem first, okay? Think about how you would do what I'm going to ask you to do. I'm going to task you with building your own ruler, and I'm just going to give you a length of aluminum. And you have no idea how long this bar is. Like, I mean specifically in terms of like meters or whatever. I want to present to you a ruler as a transducer. All right, so this is a little abstract to think about. I mean, it's a little different than like the photoresistor circuit where it's clear. Like I have light intensity coming in, and as I change that light intensity, it changes the voltage that comes off. What is that relationship for a ruler? Well, at least the output, the way I see it, you have the ratio of some object's length to the length of the ruler. That's what a ruler outputs for you, like when you're measuring something. I mean, there's tick marks on the ruler, right? But those tick marks represent the calibration equation between this output and, well, the object's length itself. So the input is, there's an object of some length that I put adjacent to the ruler. And then the output, like we don't have any tick marks yet. We don't have a calibration equation. All we can see is there's the ratio of this object's length to the length of my ruler. Airbus says there's no such thing as a meter. Okay, I mark the aluminum bar at intervals of 1/10, and then I use it to beat anyone who says we should measure things in... Okay, fair enough. That is a solution. Isn't a meter defined as the distance traveled by light over a certain time interval? We'll get to that. That's part of the story, okay? We're going to get into this story. It's very interesting. So, I mean, when you think about it, if I was going to make my own ruler, the easiest thing I would do is I would grab another ruler, right, that I think is reasonable, and then I would mark the aluminum ruler with the tick marks from this reliable ruler. But how did they make that ruler that I'm using as a reference for my own ruler? So, okay. To calibrate, I need something of known length. And that's kind of what I'm getting at with a ruler. Like, I could say, hey, I know that this ruler standard is like 12 inches or a meter stick. And I say, okay, this is a meter. And if I put that next to my custom ruler, I can look at the ratio of that meter length to the length of my ruler, and that gives me a starting point to start putting tick marks on my ruler that mean anything. But I need something of known length. But then, like I said, chicken and the egg. How was the first ruler ever made? What did they use of known length? So here, this is where the story begins, and it's very, very interesting. Yeah, a foot, a person's foot. I mean, that's where foot comes from. We're going to start with the metric system, though. Yes, hands, feet, fingers, but you can see this gets tricky. It gets tricky. Okay, so at some point, people had to arbitrarily define an object of some length. And we're going to talk about the story of the meter. There has to be a beginning. There had to have been the first ruler, the first known length. And so if you go back, you had to come up, you had to start somewhere. And the answer is they just made it up. Okay. Around, we're going to start at 1789 here. And this is like prior to 1789, maybe a couple decades prior. Isn't the case similar for degrees? It's going to be the same with anything. You can do a deep Wikipedia dive on anything that you can measure, and you're going to find a similar story. Everything is made up, nothing is real. Hey, don't go crazy. Don't go crazy. Okay, around 1789, a meter was defined as, this is interesting, the length of a pendulum that has an oscillation period, or rather a half oscillation period of 1 second. Okay, think about what this means. You have a pendulum of some length, and we know that the frequency of oscillation of a pendulum doesn't depend on the mass at all. And so let's say it swings over here and then it swings back and so on. You know the story of a pendulum. So a full period of oscillation is the time it takes for it to go to one side and then come all the way back. So they said a meter is the length of a pendulum where when I release it, it takes 1 second to get over there. So check this out. So 1/2 of the oscillation period, which I'll call capital T. How do they make a second? That's a good question that I actually don't know the answer to. Because you could go down this same rabbit hole with time. Legend has it Joe Mook was the one who invented a meter. I don't know, could be. Okay, so 1/2 period is 1 second. So that means that the full period of oscillation is 2 seconds, right? We know that the period of oscillation is 1 over the frequency in hertz. So the frequency of oscillation is 1 over 2 seconds, and that's 0.5 hertz. That means half a cycle per second, right? The frequency of oscillation in radians per second is 2 pi times f. So if we take 2 pi times 1/2, that just gives us pi radians per second. Now you guys have modeled an undamped pendulum before at some point in your dynamics career. We all have. But the frequency of oscillation of an undamped pendulum is the square root of gravitational acceleration over the length of the pendulum. So let's solve for the length here. Gravitational acceleration over that natural frequency squared. So gravity is like nominally somewhere around here, 9.81 meters per second squared. If you divide that by pi squared, so that's radians squared per second squared. If you do the math, you get 0.99 meters. Isn't that cool? That it comes out to what we now consider basically a meter. Okay, this is where the story continues, okay? Because they didn't stick with this. They didn't stick with this. You may or may not know this. Thankfully, they didn't know how to measure anything less than a second. So so it's not 1. Yeah, it's not 1. Okay, so but gravitational acceleration varies slightly around the planet, depending on where you are. So that means that somebody in France and somebody in the United States, I don't know, the meter is different depending on where you are, if you use this definition. Why do anything outside of Paris? Jean-Claude, I can't see why you would think that. Okay, so guys, they made a new definition for the meter, and this one is actually a little bit ridiculous. This one's a little bit ridiculous. In 1789, a new definition. I kid you not. One over a million. Like, this is conceptually what they defined a meter as. Times, and here's like a paragraph in here. Distance from North Pole to the equator. And guess where you pass through? Passing through, you guessed it, Paris. And we're assuming a flattening ratio of 1 over 334. So basically, you like flatten down the Earth to a plate with a certain ratio. We won't get too much into that, but they chose some geographic distance as a meter, and because the Earth is flat, by the way. And then, because how are you actually going to measure this distance? Here we go. They fabricated a platinum bar. Somewhere close to this length. And they called this the standard meter. So here's the important thing. This physical bar that was in Paris is defined as a meter. It's like a physical object. So it is just arbitrarily defined as that. And so if you wanted to make a new ruler, you would have to use an object of known length to calibrate your ruler. You would actually have to go to Paris and use this one physical object, which is the standard meter. So obviously that is really inconvenient. How did they know that distance? I don't have a good answer for that. It is kind of impressive. But they built a platinum bar estimating, like, essentially what they thought that distance was. Because in 1789 they were better at math. That could be. Okay, let's go back. Okay. In 1889, so this is 100 years later, they made 30 copies of this bar. 30 platinum iridium copies of the bar. And they distributed them worldwide. They distributed them across the world. I think the United States got like number 27 or something like that. And it was very difficult to fabricate these bars because they had to be like, exactly the same. I think they estimate that each of these bars was within a micrometer of the original. So they were like pristinely fabricated because this is a holy thing. This is a meter. If it's off by a little bit, that really screws things up. Okay, the story continues, guys. So around this time, like around the same time that they shipped these 30 copies around the world, scientists were doing spectroscopy experiments. Now, I'm not a chemistry expert, so I really apologize if any of you guys are experts in spectroscopy. But the idea is that different elements absorb different frequencies of light. Absorb or emit or whatever. They react to light in different ways. And spectroscopy is a way of studying like what specific frequencies of light that different elements react to in stronger or weaker fashions. All right, so one element that they were looking at was cadmium. And they were doing spectroscopy, so they're shining light. Spectroscopy, hey, welcome, not prof. No, not colonoscopy, berserk, okay? It's different. Okay, so cadmium, one of the elements they were studying. All right, and so it turns out that cadmium emits a wavelength of light in kind of the red spectrum. So let's draw a red wavelength. Okay, and what these guys were trying to do, now I admire these people because what they were trying to do is measure the wavelength. So the peak to peak distance of this wavelength of light. Now these scientists, don't ask me how, because I don't really know. They determined this wavelength to be, for cadmium, 643.847 nanometers. And in order to get this measurement, they had to compare this to the standard, the international meter standard. So this quantity, it has to be related to the length of that physical platinum iridium bar. So what this number means, if you think about it in terms of calibration, is this scientist had to connect all of these waves end on end on end and see how many waves it takes to make up the length of this platinum bar that we call a meter. And then if you divide that out, you find that each wave took 643 nanometers. Which is just insane to me. I don't know. I need to look more into this. I'm just giving you the story right now, but you can look more into the details. Okay, guys, the story. This is interesting because this is where the story takes a turn. So this person used, there's 30 of these bars out there, right? And he used one of those bars to determine this length. What they did is they compared this to, I think, like the original platinum bar in Paris, and they found that this was off compared to that bar. So, okay, compared to one of the bars, or basically they just found this measurement inconsistent across the bars. This measurement inconsistent. Like maybe for one bar, it took 1,000,001,001 wavelengths to cover the length, or something like that. Inconceivable. I know. Okay, so here's where they made a good decision, though. Instead of redoing the experiment, actually, you might consider this a cop-out. They redefined the meter at this point in history. So that it was consistent with the experiment. But this actually makes a lot of sense. Because if you think about it, like cadmium, it's easier for somebody to run an experiment with cadmium and measure the wavelength than it is to get your hands on one of these 30 bars. So this is a way of like making it more global. Like everybody can get a standard, can get their hands on this standard, basically. All right. And so now we're kind of working our way away from these physical objects for the standard. And in 1960, we changed the definition again. but still on the same principle, based on the wavelength of krypton, unrelated to Superman. It's not kryptonite. So I guess krypton has a more consistent, it has more consistent spectroscopic properties. So this is even more consistent. Krypton has entered the chat. This is MAE334, right? Yeah, okay, we're talking about calibration, okay, and this is a really interesting story. Okay, so this is the final stage in the journey, at least at this point. So in 1983, updated once more. This is the final step in the story, okay? The meter is now defined according to the speed of light. And as I was compiling this story, I actually ran out of time to like give you this definition. I'm going to find it on... We're going to find it. Oh my goodness. Okay, we're going to pull this up on Wikipedia. You're going to love this. Be patient. Be patient. Here we go. The meter is the length of the path traveled by light in a vacuum during a time interval of 1 divided by 300 millionths of a second. And the justification is just once again that this is something more consistent that we can base it on. But it's just fascinating to me that, yes, the meter started as something totally arbitrary. And actually, if you're wondering, like, why is there this bizarre number here? Like, actually, it is pretty close to 300,000. It's because they tried to stay pretty close to what the original meter was. Like, even as the definition has changed, like, even if we go back to the very original definition here, well, this isn't the original, but Paris in 1789, even that, like, this M is the modern day meter here. Like, even this definition is pretty close to our understanding of what a meter is. So even with these definitions, it hasn't changed much, but it's important that it's something consistent. Okay, we're going to finish up right here. Just a few closing comments. So let's review these steps really quick, because this is what you're going to do in the lab. You're going to be calibrating an accelerometer. You're going to be applying known external stimulus to this accelerometer, which is going to be known, and I'm going to say air quotes here, known accelerations, because we're going to use gravitational acceleration. And we're going to assume that it's, 9.81 meters per second squared, which will be pretty close, but it's not exactly known, perhaps. So you're going to apply known accelerations to the sensor, and then you're going to record the voltage that comes off the sensor. You're going to repeat this for a bunch of known accelerations, and then you're going to make a plot. Actually, I'm going to have you make a couple plots. And then you're going to come up with a calibration equation, and then you're going to use this calibration equation for a couple tasks that I give you. But it's cool. Yeah, if you're interested in a good read, just look at the history of the meter. I didn't even give you all the juicy details. This is just the spark notes. I'd be interested in how time is measured. Other quantities. I mean, think about weight. There's a standard kilogram that was sitting around there somewhere. So the main point, get baseline for measurement and Earth. Wait, the second part, you said Earth is flat for the second part. I mean, I agree with half of your statement. Trent says, what do you want us in the online section to record for the time lapse for workshop 2.1? Just the assembly of the circuit. Paul says, time is a construct, man. Hey, time is important. All right, everybody, that wraps up our discussion for today on calibration. That's a story about the meter. It's a cool story. You're going to apply this in lab this coming week. Be looking this weekend. It's going to be up there. The procedure. I'm going to post a little video for all of you online or in-person students to see myself going through the procedure. I'm a Toaster says, I'd be interested in the sensors being used on the Mars rover. Yes. Yes. I'm interested in that as well. I mean, different types of sensors for different things. I mean, like I heard some of the first experiments that they're doing on Mars is they have a little UAV. Or like a little helicopter, actually. And they're going to run some tests of using like an autonomous flight test with this helicopter. And I'm assuming it's standard sensors on there. Inertial measurement unit, accelerometers, gyroscopes, probably magnetometers. Ooh, check out Mark Rober on YouTube. He has a couple videos related to that stuff. I'll have to check that out. Oh yeah, sorry Mobius, I disabled hyperlinks. Mark Rober. Oh, just Wikipedia links? Is it on the Mars rover? You can throw him in the Discord. Mark Rober is good. He was former JPL engineer. Oh, nice. Yeah, throw it in the Discord too. I'd be interested. Yeah, I think that's so cool. They had a sky crane to lower the rover to the ground. Oh yeah, that's a huge collaborative project. Hundreds of people, maybe thousands. I don't know. I hope you guys are having a great Friday. This is the end of week 3 of classes at UB. Can you believe that? Time is flying. Best class this week, awesome. Glad you enjoyed it. He made a self-aiming pool cue. I'm gonna have to check that out. Wait, is this the same person that made that glitter bomb? Because I've seen that. That's funny. Yeah, I saw that. That's actually, after this class, you guys could definitely make one of those. That's not. You could make a version of that. Can the online students buy an accelerometer and do the experiment for bonus points? I won't give you bonus points, but accelerometers are really cheap. I think that's a great sensor to pick up and play with. You did a quicksand hot tub? Hey, see you later, Lil Kev. Your phone has one, and you might be able to find an app that lets you see the raw output from it. Yes. Yes. Mildew, have a dandy weekend. Yeah, I'm sure there's a free app. There's got to be a free app that lets you tap into the accelerometer. Have a good one, T-Sizzle. Your Nintendo Switch has an accelerometer, a gyroscope in there. Hello, Not Prof. Wait, what's the emote for Sandy? Yes! Wait, I thought I... Oh, I didn't do a capital C. Well, you gotta do capital S, capital Z. There you go. All right, everybody. Thanks for hanging out today. You'll be hearing from me very soon. Oh, that pulls up the emotes automatically. I didn't know that. All right, I'm gonna sign off, my friends. See you soon.